I wanted to mention two more things though about scattering. And they're in the notes, and I didn't mention them before, but I do want to mention them just before we leave the topic of scattering completely. Point one is that tunneling through a barrier. Oh, the other announcement is do the quiz. There's a quiz as usual. So okay, but and this is related to the quiz, I guess. If you have a potential step like this, and say you're doing scattering with this energy here. Remember how it goes? We have these coefficients A and B in here, and then here in region 2 we had C and D, and then F and G, describing the e to the plus or minus ikx's, e to the plus or minus ikx type solutions. And in here, because the potential is higher than the energy, you would get E plus or minus kappa x as the fundamental solutions that you'd have to put together and match and so on. And we introduced this M matrix, which takes you between the coefficients F and G and A and B. And for scattering here, we might be interested in, an incoming particle, some plane wave. We only want, maybe to know the transmission probability of the particle making it through this barrier. And in that case, in the usual thing we do is we set the incoming wave to 1, the amplitude, and the B part is the reflected portion. And then we have this matrix M, and then we know that out here, we only want the transmitted portion, that we don't want anything coming in from positive infinity. So we set G equal to 0. And if you work out what this vector is, right, if you write this out in components, then you would get that this is the M11 component multiplied by F, and then this is the M21 component multiplied by F. So this equation up here tells you that F, which is the transmitted amplitude of the scattered portion, it's the transmitted portion of the wave that makes it through the barrier. That's equal to 1 over M11. And you can work out what M11 is explicitly. And when you do that, you'll find that the transmission amplitude squared, which is the sort of probability that the particle is transmitted, is 1 over, and you'll work on problems like this on the homework, but it's a simple procedure of just matching here and doing matching the continuity of the wave function in the first derivative, the logarithmic derivative, and you find that this is kappa squared plus k squared over 4k squared kappa squared. And here you get a cinch hyperbolic trig function here of kappa A. This thing kind of blows up exponentially. And if kappa A is very big, then this exponential part kind of dominates the cinch function. And what you find is that this whole thing is approximately equal to 16 kappa squared k squared divided by kappa squared plus k squared squared. So just the inverse here, and you get an extra factor of 4 here. But the point is that this cinch squared, what happens to it is it becomes an exponential squared, and so that gives you this 2 minus 2 kappa A, because it's 1 over the same. So this starts to dominate. So basically, when this condition is fulfilled. So you get an exponential decay of the transmission amplitude, which makes perfect sense, right? As you make this, and this is the size of the barrier is A. So it makes sense that as you either make the barrier higher, which would increase kappa, remember that's related to the square root of the difference between V and E, or you make it wider, then your transmission probability gets exponentially suppressed. And so because of this idea of the M matrix, that we can use it to connect coefficients here to coefficients there, you can also kind of, you can do that for a series of these steps. You don't have to just think about one step. You can imagine any kind of potential, say like this, some complicated potential. You can imagine breaking it up into little rectangles, which are little square barriers like this, as an approximation to what happens with the scattering. And so then what would you do? Well, you would go in here, here's your energy, say, that you're coming in with. You would identify these so-called classical turning points, sort of classically the particle would just reflect. And then the probability of making it across here, across this barrier, right, would just be kind of the probability of making it through these little square guys. And you can put in more of them as you want to make the approximation more and more accurate, right? And in the limit, you can put an infinite number of them. And the idea is that the probability of transmission will be given by approximately, if we ignore all this stuff out front, the product over these different boxes, these boxed barriers, of the exponential of -2, and then kappa evaluated at x sub I at each of these little rectangular barriers, whatever that associated kappa is. Remember, it's just the height of this thing, basically, with the square root and appropriate factors of h bar. And A could be just the size of these little rectangles that we put in, so it's delta x. And in the limit that you make the rectangles very small and numerous, of course, well, first we could write this as a sum inside the exponential, right? A product of exponentials is the same as summing up the stuff in the exponent. Some of the arguments here, you got a 2 out front here, you have the kappa x sub I, this is delta x. And this, if you look at it, is a function, kappa, which is, the difference between E and V along this curve here, approximated by these rectangles. And this is the size of the little rectangles. And so this just, if you think about it, as the height of the function times the little width of the rectangle, that's just a Riemann sum for an integral. It's discrete approximation to an integral. So as you make all of these rectangles numerous, you add, oh, I forgot a little minus sign. If you add very many of them, then this becomes just the exponential of -2 over h bar, the integral from x1, we'll call it, which is the first turning point, and then this x2 is where the energy passes over here. It's the integral from x1 to x2 of kappa x, now treated as a continuous function that describes this potential in that region dx. So that's just a nice way of calculating the transmission probability for any arbitrary potential. It's because the transmission probability will be dominated by this exponential. That's going to dominate the behavior of the probability, because it's a thing that's varying most with kappa and so on. And so a pretty good approximation to transmission probability for a kind of arbitrary shaped barrier is this exponentiated integral of kappa. And this has lots of nice applications to things like nuclear decay. You can imagine some particle confined in a potential well somewhere, and in the nucleus, and there's a potential barrier to having it escape the nucleus in a decay process. And if you want to know sort of what the probability of that decay is, then you might calculate using this formula what the transmission probability is across the arbitrarily shaped barrier. We'll get more into that later, the exact dynamics of such a process, how it can happen. But I just wanted to show you this nice approximation for tunneling over any arbitrary barrier. You identify the classical turning points where the energy crosses the potential, and then you integrate over the stuff in between the barrier part. You can do that for any arbitrarily shaped barrier, and it gives a pretty good approximation. Provided again that the sort of the barrier is high enough. Yeah.
Is in the kappa value, you said it was just the height, right? It was a square root of something over h bar, right?
Yeah, it's however, yeah, it's square root of v minus e. Kappa is proportional to the square root of v minus e, you know, with the appropriate h bars attached.
Okay.
And there's an m in there too.
So I was just thinking that because, you know, that integral is pretty easy. I mean, that's why when I saw you were doing that Riemann sum, I figured, oh, that's an integral that we're just going to take, you know, but you really need to know what those values are. So
yeah, you need to know the shape of the curve, you know, and then you take its square root.
Yeah. Easy. All right, thank you.
Well, yeah, so, oh, yeah, see, I sort of got mixed up here. So there's no h bar. I'll tell you what it is. It's okay. So the h bar snuck in there is because kappa is equal to 2m over h bar. Right? That's what it is. So you can stick in this kappa into here. Yeah, I don't know how I did that. So, so h bar squared. So it's 1 over h bar times square root of 2m. Can put an equal sign there. Yeah, so you get a 1 over h bar in the exponent. All right. And that's actually a very important thing, which we'll talk about next semester, which is you'll very often find that in quantum mechanics, you can construct quantities such as transmission probabilities that have like this 1 over h bar and an exponent times stuff. And this comes up when we'll look at the path integral. And it's interesting to think about the limit that h bar goes to 0, which you think about as a kind of classical limit. If you think about it here, right, as we send h bar to 0, this blows up and you get, you know, a big number. So the probability should go to 0, right, as h bar goes to 0. So that you can just see that from this expression. And that should make sense because, you know, you do the quiz, but, you know, classically, you're not allowed to cross the barrier like this, right?
Yeah.
So we'll see when we do path integrals that the h bar goes to 0 limit is it's a classical limit. And you see a little bit of a reflection of that in this approximation for scattering across an arbitrary potential. Okay, and the other thing is point 2. There's this interesting property. There's a connection between bound and scattering states. So of course, for the harmonic oscillator, we'll be looking at bound states, again, part of the quiz. So take the quiz when you can. there's a connection, actually, a pretty deep connection between scattering and bound states via the S matrix. Why? Because, all that's happening for a bound state, we still, I like to think about this, as the regions 1, 2, and 3 kind of thing. And the only real difference for bound states, right, is that out in regions 1 and 2, your energy is smaller than the potential, right? This is for bound states. In regions 1 and 3, the energy is smaller than the potential, so you get exponential decays of the wave function. You get, the psi of x decays away in regions 1 and 2. And if you think about what that means in terms of the sort of fundamental solutions here, remember we had A and B here and F and G out here. And these were associated with, plus or minus IKX for scattering. That's for scattering. But for bound states, all that happens is your K gets replaced with I kappa. And so the coefficients A and B now correspond to, instead of plus or minus I kappa x, if we stick in I kappa, they correspond to the coefficients of minus plus, right? Because I times I will give you a minus sign, minus plus kappa x. And out here, F and G will also correspond to minus plus kappa x. And if we think about what a bound state requires, what does it require? Well, it requires exponential decay. So it sets here it would set the A coefficient to 0 because that would correspond to minus kappa x, and we have negative x out here. This is minus x, and this is the plus values of x. So out here, you don't want the wave function blowing up for negative x. It can't blow up like that. So you have to set A equal to 0. And out here in region 3, you have to set G equal to 0 because you don't want the plus kappa x solution because that will blow up with increasing x. So both of these are equal to 0. And if we recall the S matrix, what's the S matrix tell us? The S matrix connects the in and out states. It takes the in states, which in this case are A and G, and connects them to the out states, which are B and F. So this is a reflected transmitter. So what would the S matrix be for a bound state? Well, it would be a really weird matrix, right? It would be a matrix that takes 0, 0, to something that's non-zero. And that's singular. That's only a singular matrix can do that, because if you think about it, it must be that 0 is multiplying something and giving something non-zero. So whatever that something is, it must be infinite, right? So it must blow up. So the conclusion is that if we take K and we replace it with I kappa, then S evaluated at I kappa is singular at those bound state solutions. So you can actually look for bound states by looking for poles, singularities in the S matrix. So bound states correspond to singularities, in particular poles, in the complex, complex analysis sense. Singularities, poles, in the S matrix. And not just evaluated for like an arbitrary incoming particle momentum for scattering problem, but with the replacement, you take the scattering vector that you would normally use and you replace it with I kappa. You look at what happens along the imaginary axis instead of just a real scattering momentum. And any singularities along that imaginary axis, if you think about K as sort of being a complex number, those singularities correspond to bound states of your potential. So the scattering and the bound state problems are kind of related to each other. So that's kind of cool. Yeah, those were the 2 points I wanted to make. Any questions about that before we sort of jump back to harmonic oscillator?
Guess not.
Well, that was good.
I mean, actually, so you're talking to the complex plane. Those are just you're just saying those poles that we find when we're doing our normal complex analysis. And we have to find, in that domain, we find certain poles, right? And that's basically
well,
in the matrix.
Yeah, remember what the S matrix is. It tells you about the scattering problem as a function of, the incoming momentum, which, K is, P divided by H bar. So it just tells you about the scattering problem of, how you connect in and out states.
Okay.
And so it's got matrix elements as a function of K. But what I'm saying is that the difference between the scattering and the bound state problem is just that instead of the plane wave solutions, you have the exponential solutions, which are constrained. They have to decay away to zero at infinity. The extra constraint tells you that the S matrix actually has to be singular for those bound states. If we think about the S matrix now as a function of imaginary K, because all that changes when you go from scattering to bound and, for a particular potential that's sort of constant out here in 1 and 3 is just that, your K gets replaced with I kappa.
Okay.
It's really the only difference, right?
Okay.
If you have some potential that's sort of zero out here and then something happens or you got some kind of weird stuff in here in region 2, 1, 2, 3, then the only difference between the scattering problem, which is positive energies, or the bound state problem, well, should be careful. It's got to actually give us some kind of bound state solution. So out here, the only difference is that out here in regions 1 and 3, K gets replaced with I kappa. So looking for bound states is the same as looking for poles in the S matrix at imaginary K. That's what the statement is, more precisely.
That makes more sense than what I was thinking. Okay.
I think it's a nice way of thinking about problems in general as in quantum is sort of the asymptotic stuff, the in and out states far away, and then all the interaction stuff that happens in sort of the region 2, which you try to do as much as possible without dealing with the the details of what happens in the region 2. It's kind of the idea of a lot of these developments. We'll see it more when we do 3-dimensional scattering next semester. Okay, well, I guess I'll just clear this. All right, so we're doing the harmonic oscillator, and where we left off is I rescaled things in such a way that the Hamiltonian now has the following form: h bar omega over 2 p hat squared plus q hat squared, where these are rescaled positions and momenta, and they satisfy the commutation relation q hat p hat is equal to I, just I times the identity. And so what we want to do is, this has the form of a kind of perfect square, right? In the sense that maybe we could somehow factorize it, right? This is kind of like a difference of perfect squares, right? You ever see something like x squared plus y squared? A good thing that you might think about doing is just expanding this out into linear factors, right? You'd have x plus iy, x minus iy. And that's kind of the motivation. That's kind of what you would want to do here. in order to try to solve for, you know, the eigenvalues and eigenstates of this thing, is the first thing to do is try to kind of factorize it. And the way you do it is you say, well, okay, we could write this as q hat, you know, minus I p hat, q hat plus I p hat. But that's not quite good enough because unlike numbers, these are operators. So you're going to be messing up because the cross terms don't necessarily cancel, right? The p times q and q times p, they're not exactly the same thing because they don't commute. So you have to subtract off the commutator to cancel out those cross terms. But thankfully, we know what the commutator is. And again, this is just subtracting this q hat p hat term and p minus p hat q hat term, all multiplied by I. So, but we know what this is. This is just, you know, I times this guy. So that's fine. It's just a constant. So it's nice in this case because you get the factorized thing, right? You get the factorized thing plus a constant, h bar omega over 2 I. And why is this good? Because now we can think about this as an operator. And these two guys are operators. And we know that q hat and p hat are Hermitian. So these two guys must be, you know, Hermitian conjugates of each other. If we dagger the p, that just becomes p. If we dagger the q, that becomes q. You know, they're observables, position, momenta. We can measure them, so they're Hermitian operators. So this operator goes off to this guy when under that operation. So this we can write as h bar omega over 2 times a dagger a, where a is this operator that we sort of factorized the harmonic oscillator potential into. Plus, of course, I over, oh, sorry. So this just, let's see, how do I, oh, yeah. So it's convention to define A as 1 over square root of 2 q hat plus I p hat. Square root of 2 doesn't matter so much, but it makes things a little bit cleaner. So it's nicer if we absorb this factor of 2 into the definition of A, because then A dagger also has a square root of 2. So this gets absorbed. This becomes h bar omega A dagger A plus I over 2. All right, much nicer. And you can check using this commutation relation that A dagger gives you the identity when you commute. And you can define, of course, a new operator, which we'll see is called, you know, the number operator, which is just A dagger A. It's called the number operator. We'll see why in a moment. But since this is the identity, right? And, you know, if we figure out how to diagonalize n, right? If we like find its eigenvalues and eigenvectors, we'll automatically have the eigenvalues and eigenvectors for h, because h is just a constant times n plus, you know, some other constant identity. So we just have to diagonalize n in order to figure out what's going on with the energy states. So let's think about that. Let's think about what an eigenstate of n would look like. We'll just label it with some nu. That's the eigenvalue. Then what else? Well, first of all, because of this funny form of n, that it's A dagger A, there's the following interesting property, that if you take the magnitude squared of the vector A nu, which would be, you know, A new dotted with A new. This is the operator A acting on one of these news. Now we can rewrite this, right? This is acting on the bra, so we can pull it out of the bra and make it an A dagger here. And we can pull this out of the ket and put it out here. Now it's just acting on this ket new. So that whole thing, right? Which now you can replace this whole thing, right, must be equal to, this is N now. This must be N acting on new, which gives us new, because just by definition. So this is new V, and of course this just must be equal to new. And so this must be greater than or equal to 0, right? Because it's the magnitude squared of some vector. So we immediately conclude, first of all, that all eigenvalues of this N operator, that they're positive. Okay. We can do something else now. We can oh, and another thing is, suppose that nu is 0. Suppose there's a 0 eigenvalue. If that's true, then an interesting fact will be that, you know, that if this is 0, that means that the magnitude of this vector is 0. So it must be that A acting on the eigenket, you know, corresponding to the 0 eigenvalue, if such a thing exists, then that should be equal to 0. It should make it vanish. So it annihilates, this little A operator should annihilate the 0 eigenvalue state. So that's another property that we have. So, you know, we're just exploring. See, it's an amazing thing. You just start with this potential, and then just through a series of manipulations, just explorations using what we know about properties of operators, you can actually derive like all sorts of properties for the harmonic oscillator. I mean, we'll see, we'll get the exact solution for all the energy eigenstates and eigenvalues, but this is sort of the procedures. This is kind of, you know, our exploration of it. And again, the key point here was trying to factorize this kinetic and potential terms, because they're kind of symmetric. They look like a difference of perfect squares. And since we're in complex land, it doesn't bother us that it's not x squared minus y squared. It's x squared plus y squared. But, you know, in complex land, we can just put in an I and factor in this nice way. And the reason it's nice is because now these two things are complex conjugates of each other. IQ minus IP and Q plus IP. So, you know, so we call this a new operator, A. We go from there, and we'll see that those are the ladder operators. But it all comes out kind of naturally, you know, if you're just given this, if you had sort of right intuition about these things, you can sort of derive everything from scratch, which is sort of what we're doing here. All right, so another property is, suppose, so already it's interesting to think about A acting on one of these eigenvectors. So we might wonder what N does if it acts on, you know, A acting on one of these new operators. Kind of natural just from this consideration, right? We see that A acting on something gives us something interesting with respect to the eigenstates of N. So we might wonder what A acting on an arbitrary eigenstate, and then what that does when we act with N. So let's look at it. We know that how N acts on nu, so it's nice to commute these two things. So you write them as commuted, and the price you pay, of course, is that you have to add back the commutator. But this is not so bad. N acting on nu is nu, and then A acting on this guy. And then you just have to work out what this commutator is. And what it is minus A. And you can work that out from just the properties of this guy and the definition of A. It's a little bit tedious, but you know, it's let's see here. It's A dagger A, you know, commuted with A. You can do those, use one of those identities that you derived in the homework, you know, where you expand this out and rewrite it as just in terms of these kinds of commutators. Not too bad. And what you find is in the end that, you know, it's minus A. But look, this is kind of cool. It means that this is a constant times the same vector again. So A nu is an eigenstate of n with one with eigenvalue nu minus 1. Okay, that's kind of cool. You can do the same thing with the A dagger, same sort of procedure. You can ask what n acting on A dagger does, and you can, again, it's same algebra. I don't really want to work it out here. Again, you have to compute n commuting with A dagger. You get nu plus 1, A dagger nu. So these A operators, what they do apparently is they take our eigenstates of n and they raise and lower the eigenvalue by 1. So in principle then, right, what could we do? We could imagine, can we have can we construct the whole spectrum by just taking an arbitrary nu and then acting with these guys, right, over and over again? Can we do that? I don't know. What do people think?
I would say, well, it's raising and lowering. A just raises and lowers plus or minus 1, right? So I would say, yeah. I mean, that would be my guess. I mean,
but look, it's really weird because we saw that the nu's have to be positive, right? So if you keep subtracting from an arbitrary nu, we know that, you know, the eigenvalue of this guy is nu, eigenvalue of this guy is nu minus 1. This one's nu minus 2. How could you, if you keep going, right, eventually you'll hit negative numbers.
You just have to like define that once you get to a certain, like the ground state, that operator acting is just 0, right?
Yeah, but there's only one way that can work. What has to be true about this number nu?
0.
Well, no, if it's, well, yeah, okay. So 0 is a possibility. If it's 0, then we know A acting on 0, so just give us 0, and then we'll be done, right?
Yeah.
So what are the other possibilities for nu? Sorry?
It just has to be a positive integer.
That's right. It has to be a positive integer, or rather a non-negative integer. Because that's the only way that you can reconcile property 5, that we can just keep acting and getting more and more eigenstates, with this property 2, with property 1, that all the, you know, first they're all positive, and that when A acts on 0, you get 0. This saves you in a sense from having negative eigenvalues, because what happens if you start with any positive integer, say like 5, then if you act with A on 5, you know, it will get eigenvalue 4. A squared on 5, you'll get eigenvalue 3. A cubed on 5, you'll get eigenvalue 2. A fourth, you know, 1. And then all of a sudden, when you take 5, lowering operators and you act on 5, then you'll get to 0. You'll have eigenvalue 0, and so it'll spit out 0. So then when you act 6 times on 5, that'll still give you, just 0 because, you know, a to the 5 acting on 5 will give you 0. So if you act with a again on both sides, it'll just give you 0 again. It'll just zero out all the ones that go negative. And that's only possible if nu is a positive integer. If it's like, if you had like 1.5 as a possibility, you'd run into big trouble, because as soon as you act with a twice, you would, you know, you'd skip 0 and you would get an eigenvalue of, you know, minus 0.5, which is not good, because that violates this thing. So the problem is like over constrained. There's nu, you can't just get anything for the eigenvalue. You can only get positive integers. And it's a general, you know, if you were to do this in terms of the kind of spatial part, you know, just solving the Schrodinger equation with x's and, you know, the wave functions. If you did that, then what's the equivalent of what would happen? Well, what would happen is you would have to make sure that your wave function is square integrable, right? So it has to vanish far away. And that would give you a constraint that you can only satisfy if these nu are positive integers. But it's much easier to see in the space of energy eigenstates, as opposed to in the L2R space, the wave function space. Much easier to do it this way. But you could just solve the differential equation corresponding to the Schrodinger equation if you wanted. Okay, and that's why it's called the number operator, right? Because of this property. So we got the number operator, and the eigenstates are numbers. 1, 0, 1, 2, 3, and so on. So H acting on one of these ends is going to be H bar omega n plus 1/2. And those are the, these are the energy levels of the harmonic oscillator. So yeah, so what else do I want to say? So, okay. Yeah, and these ends are the energy eigenstates. And you can go between them by applying the raising and lowering operators. Okay. And you can even work out what the kind of normalizations have to be when you act with these raising and lowering operators. So let's suppose we look at how A acts on, say, the n plus 1 state. So we know that this should lower it by 1, but in principle, there could be a some coefficient out front, C. And we also know that if we do A dagger A acting on n plus 1, that should be C times A dagger n, right? And this whole thing, because this is the number operator, should be n plus 1, n plus 1. And so we see from this formula that n plus 1 is kind of uniquely related to n, right? It's C A dagger n divided by n plus 1. So this guy is sort of uniquely determined by the previous one. So this is what I mean in a sense, the raising and lowering operators do construct the full spectrum. And so if you ask, are these energy eigenstates degenerate? Well, if you can prove, for instance, that the ground state, the zero state, is non-degenerate, then everything else above that state must also be non-degenerate, must be just a unique state corresponding to that energy eigenvalue, because the raising operator uniquely connects, the previous energy level to the one above it. And moreover, you can, of course, fix the normalization for these things. Well, we know that, for instance, if we take the magnitude of A dagger n squared, well, then we know that this thing is n A dagger n, which should give us this multiplied by that, right, is should give us n plus 1 out front. So you'd get n plus 1 and yeah. Here, I'll add one more step. So we can commute these two things, right? We can commute these two things past each other. And so you get n A dagger A instead, and then this becomes plus 1 from the commutator. Again, from this commutator between A and A dagger. And we know n is A dagger A, so we're commuting them to get back the n operator. So this is the n operator now plus 1, so this whole thing is n plus 1 and n. And if these are, these are going to be properly normalized eigenvectors, so we want the magnitude squared of A dagger acting on n to be n plus 1. So that tells us that, A dagger n should be some complex number with magnitude 1 times the square root of n plus 1, n plus 1. So that's the normalization. And in general, you could just write out, and I'll put in green all these properties that we have. So again, we have, these are the energy eigenstates. We can get between them by applying the raising operator. These are the energy levels. And the other bit is how these raising and lowering operators act on the eigenstates. And what these are is there's a phase convention that's chosen. The phase convention is that, this is just square root of n plus 1 with no other complex phase out front. That's just how they're defined. And this one, you can check that the normalization has to be square root of n minus 1. You can check it using the same kind of, by analyzing the magnitude of this vector squared. Same as it did for the dagger. And the other thing is any n can be constructed by applying the raising operator enough times. And each time you operate with the raising operator, it introduces a square root. So you have to cancel out that square root. So you divide out by 1 over square root of n factorial. It cancels out all these factors. And otherwise, it's A dagger, acting n times on the zero state. And the zero state is the ground state, which, as we can see here, is energy h bar over 2. So those are the kind of properties. And the only other thing is left to discuss is what about the degeneracy? And as I argued, since A dagger uniquely connects, all the states to the ground state, you just have to prove that the ground state is non-degenerate. And the way you do that is you have to go back to wave function land and try to solve for the ground state there and prove that it's unique. That, again, degeneracy is, whether are there multiple states with the same eigenvalue. So let's talk about that, the ground state degeneracy. And this will connect us back to, wave function land. In wave function land, your Hamiltonian H is, minus h bar squared over 2m. Derivative with respect to q, the coordinate squared, that's the momentum, plus 1/2 m omega squared q squared. And we can do the same kind of rescaling that we did before for the p and q. And this is now, in L2R space. It's the same space. There's different representations, the harmonic oscillator, whether in terms of a wave function or the energy eigenstates. So this is what it is in coordinate representation. And it can do the same thing where you rescale things and introduce this new variable u, which is a rescaled position, and the momentum piece, so the derivative with respect to q, becomes minus I square root of h bar m omega du, it's derivative with respect to u. Make that variable change, and this becomes 1/2 h bar omega minus d squared du squared. Just writing out this derivative now, plus u squared. It's very similar to the rescaling that we did to get p hat and q hat. Exactly the same. It's just you make things dimensionless so that you instead of p hat, instead of h bars running around between the p's and q's, you just have p squared plus q squared. In position space and coordinate space representation, you just rescale in the same way the derivative rescales like this, and then q just from q rescales like that. You just get this, which is this is like the coordinate representation of p hat squared, and this is q hat squared. Same kind of deal. So this is the thing that you want to do, and you know that the ground state, right? What's special about the ground state? What's special about the ground state is if you act with it a on it, then you just get 0. And now we can look at this in the coordinate space representation. We can put a little bra u here, which is the coordinate u, a rescaled q, and see what that means. And a, you know what a is. We wrote it down. A is up here. It's q hat plus I p hat, right? And now we just identify that in coordinate space, this is p hat squared, and this is q hat squared. So q hat is u, and p hat is minus I d du. So and a is, let me go back up here and make sure I get the signs right. A is 1 over square root of 2 q hat plus I p hat, right? It's 1 over square root of 2 q hat, so it's u minus I d du. Let's see. Make sure I have it right. Yeah, I'm trying to figure out if I got the signs right. Well, okay, so not sure about this I.
Aren't you just doing U substitution here from the top? So, and that's why you put the I there. Is that, but you're not sure if it's a plus I, because the original wasn't the original minus I.
Yeah, I'm just trying to make sure that. I am missing. I'm missing an I. Duh. Okay, sorry. It's plus IP, right? I'm missing this I, so it's times, this is, if this is P, then this is all times I, right?
Mhm.
Okay, good. This is 1 over square root of 2 U plus D du there. Great. So what does that mean? It means that in position space, this equation, what is it? It's 1 over square root of 2 U plus D du acting on the wave function representing the ground state as a function of U. That has to be equal to 0. And that gives you a unique solution. The unique solution to this equation is, properly normalized 1 over pi to the 1/4 e to the minus u squared over 2. It's a Gaussian. And there's only one solution. There's one properly normalized solution because there's just one derivative there. So, theory of differential equations tells you that there's one solution, or, one fundamental solution and one sort of normalization, which you pick. And it's this 1 over pi over 1/4, make it square integrable. And so you get the uniqueness of the ground state just from the differential equation. So we conclude from here that the ground state is unique. And if the ground state is unique, then all the other states must be unique because we can construct them all by applying the raising operator over and over again. And moreover, you can actually figure out what the wave functions are. Well, the wave functions as a function of u, again, it's like x, but this rescaled coordinate. What are those things? Well, it must be 1 over pi to the 1/4, right? 1 over square root of n factorial. And then what you do is you just apply the raising operator over and over again. And a dagger, right, is 1 over square root of 2 in coordinate representation of u minus d du. Because remember that A had plus IP, this guy would have minus IP.
Mm-hmm.
Right? Yeah. So this will give you a little minus sign there. And so this is an operator which you can apply over and over again to the ground state. It's in coordinate space. So you would get a square root of 2 to the n, however many times you apply it. And here you would get u minus d du acting n times on what? This little Gaussian guy. You do it over and over again, and you get the higher and higher energy levels. And what you find is, because the derivative of a Gaussian is just the Gaussian again times, 2u over 2, so times u. You do this over and over again, you end up getting some polynomial in u times the Gaussian again. So if you work it out, what you get is this factor out front, square root of 2n factorial. You get the Gaussian bit again because the derivative of a Gaussian is just a Gaussian, and u times a Gaussian is a Gaussian, so it just comes out. And out here you get something called the Hermite polynomials. I guess that takes me to the end of our time here, but this is the general form of the wave function for the excited states of the harmonic oscillator. And again, these states, as we found, what are they? We can draw a little schematic of the potential, right? They're evenly spaced, as we found by studying this number operator. And the first one is, a distance h bar omega over 2 above 0. And then all the other ones are spaced by h bar omega. And these have wave functions phi 0, phi 1, and so on. We got all that structure just from our understanding of, operators and commutation relations. Kind of amazing. So I guess next time we'll do a little more with this, but yeah, that's basically the harmonic oscillator.
Could you remind me how you got that pi to the 1/4 again? Or-
Well, so we know that the eigenstates have to square integrate to 1, right? Because 0, 0, I can stick in a little du here, completeness relation, in terms of that rescaled coordinate. So I should get that, psi of 0 of u square integrates to 1. Just definition of eigenstate of one of these bound states, discrete bound state, has to square integrate to 1 the wave function does. So this is the equation that this phi, that this phi has to satisfy. It's got the general solution to this equation is just, a e to the minus u squared over 2. So we're just setting a to make sure that it square integrates to 1. So that's what the 1 over pi to the 1/4 is.
Okay.